Chen telling us about thermal metastability and area laws.
This is turn on. You guys can all hear me?
Yes.
Okay, thanks. Thanks for a nice introduction. I'm Anthony. I guess funded by Simon CIQC as like a Simon CIQC postdoc. Yes. So I guess throughout the year I've also spent some time visiting MIT. That was kind of under the CIQC umbrella. That was pretty fun. But this project is sort of done really locally around here at Simon's. So it's really has been a very fun environment that's provided by the institute. And also, so this project is really, this result actually came out more of like a surprise. And it was really fun to learn about metastability and area laws from Thiago and Umesh. And this is really a topic that I probably wouldn't, came up with and try to pursue on my own. And I guess throughout the week we have seen kind of a lot of these discussion about quantum advantage, computation, quantum simulation, how do we use quantum computer. And so this is maybe a slightly different way of using quantum computer. We just sort of borrowing the mathematical reasoning kind of style of reasoning from quantum computing in order to try to say something about universal structures in low temperature phenomena. Okay, so that's probably a bit different. Maybe the setup might be unfamiliar for the computer science-minded people, so I would actually spend a little more time on just set up the problem. So the few 10 slides would be a little soft, I guess. Okay, so just to warm up, so let's look around the room. And then, a lot of these things you're looking at, they're pretty stable, right? They're probably the same as what they were like 5 years ago. Right? So you can say they're stable and maybe they're metastable. Huh? And then in particular, consider this piece of board, which is some kind of plastic, right? I would say it's pretty stable or metastable. And now I want to ask this question. So if I draw like a little box here, so this piece of plastic, this is called a set of atoms A. We can ask sort of what are the generic kind of correlation you could have with everything outside, right? So A is this guy and A bar is the complement, it's like everything else, right? So this very famous idea of area law is a claim that so the correlation between these two is actually very special, and somehow it's sort of only through the boundary. So if you count the bits of correlation, it's only scaling with this boundary length. All right, well, sort of in the worst case, you could have sort of every point is correlated with other. Okay. So let's do a poll. So if for this piece of material here, who believes it satisfies the area law? Okay, 1, 2, 3. Right. Who believes it satisfies the volume law? Okay. Who don't know what the area law? I have not heard the area law before? Okay, thanks. That's very helpful. So this is sort of like a warm up to guide sort of the physical kind of motivation behind this work to understand what are really the structures of these things you see that looks stable but maybe not truly thermal. Okay, so let's begin. So let's say you want to study something at low temperature. It could be this piece of board or anything, your coffee. This is what the approach that physics textbook often say. If something is stable, it probably is in the equilibrium. And why don't we just take it as the true equilibrium, known as the thermal state or the Gibbs state? Right? This is like actually surprisingly a simple object to define. You only need two parameters, right? Temperature, and often you can do it inverse. Inverses like 1/T. That's beta. And another parameter is just a Hamiltonian, right? This sort of describes the physics of your system. That's very important. And today we're just going to stick to whenever I say Hamiltonian, it always means sort of computer science style Hamiltonian. So it's few body interaction. And each qubit has been interacted by few terms. So this include like 2D lattice, but also kind of expander, kind of constant degree expander graphs. But unfortunately, this doesn't yet cover chemistry models. Right? Chemistry, kind of everything talks to each other. So this doesn't, our result doesn't apply to that immediately. But nevertheless, so this family actually captures a lot of very interesting phenomena, even though it looks very simple, right? This is because if you look at this, anyone with a computer or pen and paper can already start working out physics, and that has been, it has been really how it worked in many cases, right? You can work out Ising model, and you kind of understand magnets, superconductivity, and modern days, these sort of topological order, these so-called quantum memories. You can kind of learn a lot really just from looking at this object, right? But but at the same time, we are kind of all aware that we're kind of ignoring a lot of dynamics as to how you actually get to this equilibrium. But nevertheless, it seems to be a minimal self-contained starting point, and you can start proving things and start exploring physics. And sort of for the purpose of today's topic, what we like a lot about this thermal state is that it's actually very structured. There's so much structure to it that actually help us. And it's often the case that these structures are just not present in the dynamics. So it's somehow the static object is much nicer. So one such example is a Markov property. Okay, so this is probably very familiar to anyone, I guess from computer science background. So any classical Gibbs distribution has the following property. So if you select a set of spins, and then you kind of draw the boundary, and you condition on that set of spins, then it must be independent from the rest. Okay, so in the example of 2D Ising model, right? So the interaction is just nearest neighbor. Then if you draw A, and then you get B just by kind of looking at this, drawing these kind of immediate neighbors, right? So these are just B's. Okay, and then you can also see that by combining these with the Gibbs distribution, you also know that you actually also know what this conditional is. It's just some conditional version of the. You can just read it out by the conditional Gibbs states. Yeah.
Anthony, I just have a trivial question, but sorry, I'm not quite sure I can see from the diagram. How do you draw the boundary?
Oh, right. So in this Ising model, it just means that it has all these links.
Yeah.
So once you select these sets, you kind of take one step.
The orange is that you've drawn a particular connectivity graph, right? I guess my question is, what are the orange links?
Oh, this is just to highlight sort of. This is these are the edge kind of emanating out of the set.
Okay.
Yeah.
Question? Does story code also satisfy such a property?
Yes. But you have to define a proper way.
What was the question?
All right. The question is does it also true for Tor code? And the answer is yes for commute. I think commuting, I believe, but certainly for stabilizer models. Yeah. But here this is all about classical. Right? You can condition on boundary, and it's all nice. Okay. This property has really been used a lot throughout. Whenever you have a Gibbs distribution, it's really important to whenever you design algorithms or you try to do anything, computing marginals, doing inference, you just need this property kind of throughout the whole paper. Okay.
The highlighted orange atoms are entangled to the white boundary atoms. Does that state that?
Okay, I mean.
The highlighted atoms.
This?
Yeah.
Well, not quite. This is just to say, these are the things going out of the set. This is just a visual aid for helping you selecting what are the boundary terms.
Oh,
yeah,
okay,
yeah.
okay. Thanks.
Yeah. Okay, so this is like this Markov property is very nice and exact. But unfortunately, it's not true in general in quantum case. It's sort of true in the commuting case, but we don't actually have exact Markov property in the generic non-commuting quantum systems. Okay, but we have something weaker and that conceptually seems similar. Is the area law for quantum thermal states. Okay, this was proven almost 20 years ago, and the statement is the following. So again, in this 2D connectivity, if you take a set A, and then you circle this set, right, in the way that I was doing in the beginning, and then the claim is that the correlation in the sense of mutual information, so it's defined precisely as some entropic quantity. Sort of this correlation in this sense is bounded by the strength of the boundary terms. And then here, so if you just count it, it's just kind of scale with how long the boundary is. It doesn't care about things kind of inside. Okay. Okay, make sense?
So does this imply proper area law when beta is constant bound? Like, is it enough to bound the mutual information to get the area law?
Sure. So this is the definition of area law for mixed states.
Okay.
Yeah, because it reduces to pure states, but here you actually have both classical and quantum source of correlation. Yeah. Because if you just count entropy, it's always going to be pretty big. It's like a mixed state. Yeah.
Sure.
But here it's really about sort of the correlation out to outside. Yeah. And this turns out to be like a pretty nice metric. Yeah. But yes, constant beta, this is area law, and it's actually extremely generally works for any graph. It's like somehow just a very clean truth about thermal states. But of course, when temperatures get lower, beta gets larger, it's kind of degrades a little bit. Yeah. Okay. And from here, you don't immediately get, at least I don't know how to get ground state area laws from this. So there's still like a tiny technical, or there's some tiny conceptual gap and a big, I guess, technical gap. Yeah. But but anyway, this area law, if you have heard about this, is really a starting point of, and it provided essential inspiration for a lot of things we do in low dimensions. You can cook up this tensor network algorithm, and a lot of the way we do physics is really guided by this idea. Okay. So far, this is all about equilibrium states. So does it really apply to this piece of board? So sort of one of the starting kind of motivation of this work is to try to be a little, try to think about this problem of whether anything is truly in equilibrium. Okay. So this theme actually has appeared a little bit in the past few days, but let's try to articulate this. So if you think about it more carefully, a lot of the physical phenomena are intrinsically out of equilibrium. Okay, so you can kind of draw heuristically this kind of energy landscape, and you can actually put a lot of things kind of here, but not here, right? So we know that the piece of glass there actually flows very slowly. Molecules react, right? And magnets flip. Nuclears decay, right? But it may take a very, very, very long time for it to happen, but it does have to happen eventually. Okay. And also, we have learned from complexity theory that sort of these ground states or Gibbs states could be very difficult, and even in classical cases, already be hard to get these, and even harder. So you could ask, if really these true thermal equilibrium are such a scary object, what is the truth? So how to think about the fact that nature also has a lot of things that's not really this true equilibrium, but somehow we still use statistical mechanics as if it's just fully correct, right? It seems to be just quite unreasonably effective in describing whatever we mean by everything at low temperature, such as like this piece of material. Okay, so surely we're missing something from the statistical mechanics, right? This e to the beta shouldn't be the end of the story. But then how do we proceed from here? Okay. So we really try to pose like a metastability question. Okay, so if you want to be very precise, there are people who think about sort of what are models for the bath, right? If you want to be very precise, you can say, okay, I'm going to model my entire system. Maybe my environment is now some refrigerator or some bigger quantum systems. And this is sort of, in principle, correct. Right? If you can simulate the whole refrigerator, probably you can also kind of just know what the true dynamic is. But we also know that often these things is really big. Right? Usually you use a huge refrigerator to cool down a tiny chip. Right? And then it doesn't seem kind of realistic to try to actually solve the dynamics of this big refrigerator. So it does get kind of complicated if you want to start from first principle. Okay, so how do we proceed from here, right? How do we capture something that's slightly outside of equilibrium? So so here I'm presenting sort of a quote I really like from a paper by Roy Glauber in 1963. So apparently he have encountered some version of this issue. He says that if the mathematical problems of equilibrium StatMax are great, they're at least relatively well defined. The situation is quite otherwise in dealing with systems which undergo large-scale changes with time. The principles of non-equilibrium StatMax remain in largest measure unformulated. While slack persists, it may be useful to have in hand whatever precise statements can be made about the time-dependent behavior of the statistical systems, however simple they may be. So historically, in 1944, Einstein and Sager have solved a 2D Ising model. It solved the Gibbs state, right? It kind of can plot a phase diagram. However, Glauber wants to know more. He wants to sort of understand sort of this time dynamics of these Ising models, and then this paper he introduced the Glauber dynamics as like a very simple, succinct model of thermalization. Okay, so. And this approach, as he said, however simple they may be, he acknowledged that this Glauber dynamics sort of may be oversimplifying, but turns out to be just so fruitful and has still been used up to today. Okay, so let's just quickly recap. So this is sort of roughly the Glauber dynamics, and if you want to act in on a two-dimensional system, you're going to randomly pick a spin. And then you're going to random flip this according to some rule that's conditioned only on its neighbors. Okay, you can look up this rule very precisely. But what's important here is the idea of detailed balance. So you can choose it in some way that obeys some symmetry of thermal equilibrium. And then it turns out this also respects sort of this Markov property we talk about. Okay. So the dynamics is actually very simple. You can run it on like 500 by 500 Ising model on your laptop. And then from this, you can actually learn a lot more for the out of equilibrium behavior. You can just see it on numerics. Right? If you try to cool it, at higher temperatures, it looks kind of randomish. Right? These things will fluctuate if you actually run it. And then when you get closer to lower temperature, there's like a phase transition points where these blocks kind of gets bigger, but they're kind of competing. And then when you kind of go all the way down, you kind of see there's like two clear kind of, I would say, some kind of well. That one is sort of the all up, the other one is the all down. So this is all very classic notions, and people really understood it very well. And you can just run it and see what happens. Yeah.
Sorry, this might be a naive question, but like I read that there is a Glauber update rule, but also a Metropolis update rule, and they look to me like they're kind of different. So how do you know which one to pick when you're running a simulation like this?
I think it depends on what you want. I think qualitatively they're more or less the same. I mean, I think Glauber is usually more continuous time. I think a lot of this is historical. So like I think people also have independently found Metropolis rule even earlier. But sort of this Glauber, when you write a paper, is intended to somehow capture some part of physical thermalization. So it's like continuous. Okay. But you can find it everywhere in the literature, and then people make their own variants. Depends on what you want. Yeah. And the rule, qualitatively, they're the same. I mean, Metropolis rule kind of look like this. The Glauber rule looks like this. I mean, they're roughly the same. You want to suppress.
So what is this a plot of?
Yeah. So to whoever understands, this is sort of the detailed yeah. So.
I just mean, what are the axes on this?
Probability of accepting a move.
Yeah. This is. Right, I'm not attempting to try to explain detailed bands, but maybe what I just say here is that there are many ways of getting detailed bands. The Metropolis and Glauber, you can pick your favorite. Okay, and then so the picture is, once you have these dynamics in mind, sort of you can imagine there's kind of these two kind of wells, and then your dynamics kind of happily mix within it. However, there's still like a tiny chance of kind of overcoming this barrier and go to the other side. Okay. So in some sense, so metastability in this 2D Ising model is sort of somewhat, some aspect is sort of understood. Okay. Okay, so that's the classical story. It's a very long time ago. And then for today, we really want to ask this question for quantum thermalization. Right? So we want to use the spirit of Glauber and as attempt to address quantum metastability. Okay? So if you really want like a self-contained model of thermalization of the quantum in a quantum world, what are the things you would like at the very least, right? So certainly you would hope your dynamics is sort of time independent, just so that you can write it down explicitly. In the classical case, this is just called Markovianity, right? This is like a Markov chain generator.
Sorry, will you define metastable at some point, or like how should I think?
Next.
Okay, good. Thank you. Yeah.
Yeah. But first, we have to define the physical process. Yeah. So that's the key, right? Okay. So in the quantum case, there's a version of this. We write curly L for Lindbladians. So these are just quantum continuous time Markov chains that generate sort of a physical map, right? So there are actually some structural constraints in this dynamics so that it's actually physical, right? Any matrix you write down doesn't need to obey positivity, for example. Okay. So these are the Lindbladians, and then you actually want additional structures for these maps. So it's always very natural to impose locality in a physical process. And in the classical case, global rule is indeed local, right? You cannot touch one of the spins. It doesn't try to, do something very long range. You could, but in the basic models, you just only a local one. And then quantumly, you can, it will be also natural to impose that whatever map you're doing should be a sum over simpler ones. Right? Okay. But most importantly, on top of these Markovianity and locality, is about detail balance. This is again, I've already mentioned this. Formally, this is some kind of symmetry imposed so that it knows about the temperature, so that the Markov chain knows about the temperature, and then this ensures that it sort of fixes the Gibbs, so the thermal distribution. Okay, and then it's kind of it's kind of amazing that quantum detail balance was only found sort of obeying these strict rules very recently, and it was just 2 years ago that with Michael Castriano, Josh Gillian, and Fernando Brandel, that we somehow have a map that has both locality and detail balance. And there has now been several kind of maps that also match this property, so you can pick your favorite ones. But at least, the point I want to make is that we now sort of have some version of things that matches the properties of Glauber, and it seems to allow us to start playing with it and try to say something about thermalization in this model.
It's like a random technical question, but when you talk about like this continuous time like framing versus like a discrete time like algorithm, like are they generally equivalent ways of thinking about the same dynamics, or are there like technical things that come up?
So conceptually, they're very much the same. But when you want to prove things, sometimes you have to prove individually. Sometimes you can compare, but yeah, sometimes there are some technical differences. Yeah. But if you want to run an algorithm, often, computer is digital, so quite often you just do the discrete version and then just hope that whatever you prove about continuous time also works. Yeah. Okay, so here really, with this context in mind, this is really, I think, a good time to start posing the metastability question. Right? So now we have the dynamics, we can ask, okay, under this self-contained model, can we say something about metastable states? Right? Here's the definition. We say a quantum state is metastable if it's approximately stationary. So just stationary states, basically. So, because L generates a dynamic, so this really just means the state, in terms of its time derivative, is changing very slowly in statistical distance. So this one is the Shatton, so the trace norm. Okay? So this also means that if you do any experiments, any observable needs to change very slowly. So this is just what statistical distance means. Okay, so this is this humble starting condition. We can now throw away the Gibbs state. We asked, could we still say anything general, just starting from this condition? Right? Should there be,
Being a metastable state seems to be a static property, but I guess this definition uses the dynamics that you choose. So how do you reconcile the two?
This is our definition. Slow changing.
But it depends on your choice of dynamics.
Yes. I mean, yes. But here, right, so here we work with, right, so we pick one, and since the math is already technical enough, we don't try to do it for 10 other ones. But in principle, you could. But here, really, the key kind of structure we impose, locality and KMS detailed band. So one particular kind of detailed bands. And then you put this condition.
So just to follow up on that question, so this is for one set of dynamics, and so intuitively, why should it satisfy some conditions like detail bounds, but is there some physical reason why I should care about that dynamics? Like, why is that the right dynamics to consider first, let's say?
This is a dynamics to consider, and it seems to be this family. So right now, these are the only ones that, and they're all roughly the same family that has these conditions at the same time.
So it's coming mathematically, basically.
Yeah. So I think exactly. One have to admit that without this structure, I have no idea how to prove how to pose any question precisely. So detail bands is really kind of appears every page in the paper, so it's extremely important.
Can you explain again how a priori it seems like the detailed balance condition would be extremely non-local in the quantum field? So.
Right. So that is sort of, I guess this is sort of why, I guess some of the difficulties of constructing this. But so the claim of these papers is that it is possible, but then you have to pay like a tail. Like these would not be strictly local, but then there would be like a decaying tail. But the claim is that this is possible, and it can be explicitly constructed.
How should epsilon scale the system?
Yeah, you'll see. Yeah. Okay. Any?
So if I may follow up on the same questions, I imagine physicists already have some intuition for what the definition of metastable should be. Do you think it somehow matches this definition?
I wouldn't say there's a definition. I think there are certainly people talk about the phenomena. But here we really try to write down like a single line definition, and then just to start from here and prove things about it. Yeah.
But that's correctly that there are now at this point multiple different definitions for the invariants which satisfy some general detail balance condition. So do you think it's possible to show that if this metastability condition holds for one of them, it holds for all of them, basically, that it's sort of only the balance?
So yeah, I believe I think there's some sense that you can wiggle this argument that you can maybe even compare one to the other. But we didn't try to work out.
There is some even unknown invariant, but it satisfies the tail balance. Like you don't even know it, but you would be able to potentially.
Possibly, but our argument has some wiggle room, but you have to, yeah.
Do you know whether this notion of metastability is equivalent to like a local minimum, like in the plots you showed, I guess local minimum?
You'll see.
Okay, thanks.
Okay. Any more questions? Okay, so here this will just be for this talk the definition of metastability. Okay. This means stationary, because we want to have some concrete condition to start with and to reason about it. Okay. So if you pause a second, I think the audience has already tried to explore this. This condition seems kind of weak, and it doesn't care about initial conditions. Right? Someone could create any state and then evolve for a long time, and then it would probably becomes metastable. And we somehow want to say something general just about this condition, the fact that at this instance the state is not changing. Right? And that seems kind of hard to do. Right, because you could really have evolved for a long time, possibly have lots of entanglement being generated, possibly a very complex state. However, there actually is a lot of structures, as we'll see. And a lot of these kind of metastability question, the way to frame is we can actually really learn a lot from this classical, also very, very recent paper on just the classical Markov chains. Okay, so that's a definition. Here's the main result we say. So we claim that metastability implies area law, at least an approximate area law. Okay. So for any metastable state satisfying the stationary condition with the parameter epsilon, the correlation between a region and its complement, so kind of think about this picture again, in terms of mutual information, is bounded by sort of 2 beta times the size of the boundary, so that's really the same area law as the Gibbs state. But then it has some correction term that depends on these parameters. It depends on epsilons and how big the region is. Okay? But again, this metastability is really the only condition we need. We don't care where it came from. Okay? It's also pretty general, that it not only works for 2D, 3D also works for things defined on expander. So we really believe this is like a generic area law because it just works for kind of under very, very mild condition of the Hamiltonian. It also doesn't care about phase transition. All the dependence on temperature is very smooth. There's not like a sharp kink when you change the temperature. Okay, so we really believe this captures some general universal behavior about physical system at low temperatures, even when they're not the true thermal equilibrium. Okay, maybe we can go like.
Is it really area law? I mean, there's a volume term that is in the exponential.
Yeah, we'll explore this a little bit. So they require epsilon to be small.
Okay.
Yeah, I was asking the same question.
Okay. Okay. Any more?
So this epsilon, it like in the actual metastable state, imagine like whatever Ising, even the classical case, would it be just a constant, or would it actually like?
Well, next slide. Yeah, it could be extremely small. Yeah.
How related is this to bottlenecks?
That's an open problem.
Okay.
Yeah.
Sorry, what index?
Bottlenecks.
About.
Yeah.
Oh, sorry. I should actually have repeated all of them. So, right. The question is there notions of bottlenecks, and the answer is in open problem slides.
You said it's independent of phase transitions, but if I was near some phase transition, would I expect there to be an interesting metastable state?
Our theorem says that if it's very metastable, we actually also have area law. It doesn't care. Yeah. So it somehow says that even your state is undergoing some large-scale, fluctuations and like long-range correlation, the correlation somehow still has to kind of spread in this way. You can only go through a boundary somehow.
Does the classical paper that you cited in the previous slide prove something?
Right, so this I will talk about. So classically, you can ask, why don't people talk about area laws in classical? Because that's actually a consequence of Markov property. So classical people have much stronger things. Yeah.
Does it hold for a small epsilon or for any epsilon?
This is for any epsilon. But the bound become useless if epsilon is not small enough.
Can you give an example of metastable state in error correction? Like when you see metastable state, what is it doing? It's the expander.
You will see it. Oh, I will give you a very simple example that I understand.
Okay.
Yeah. Okay. Okay, we're happy. Okay, so let me just clarify some of these parameters. So the audience have questions of what is this meaning? Is this actually useful, right? First, if you take epsilon to be 0, exactly 0, the bound actually recovers of this previous area law. right? So at least asymptotically it goes to the right limit. Well, but when epsilon is not 0, it's just small, the area law only holds sort of roughly in this scale, right? If you just convert this, you realize kind of, it scales logarithmically with epsilon. So you might complain, as a CS person, you might say, well, the scaling doesn't seem very good. But in some sense, you will see this is pretty natural, because what we're asking for is like a worst case mixing time. The system you have might be some crazy complex Hamiltonian, right? And somehow this e to the a is manifesting some kind of local mixing time that's required to mix the system. Right? So we'll kind of repeat this term a little bit. But we also believe that physically, if you actually do experiment and try to see how this actually should scale, it might actually be faster. So here we're just showing like a universal bound.
I guess you don't have any sort of counterexample that suggests this might be time.
Next slide.
When you say like worst case local mixing time, do you expect this to be the actual scale of the mixing time for something like?
It's very close, yeah.
Like I don't know, like expansion or something.
For Ising, yeah. Next slide, yeah. Okay.
Is there any relationship between sigma and the? I mean, in terms of one node?
Oh, that could be very far. Like Ising, in this Ising model example, if you have two wells, it would be like order 1.
Yeah, and that epsilon will be a constant, right?
Oh yeah, but it could also be even worse. Like if you have more, this kind of local minimums, then it could just scale with how many they are. So they could really be statistically very different. Okay. So let's move on. Right. So the question is, how small could this epsilon be, right? For our bound to be interesting, you better hope A could be pretty large regions, right? So, our theorem doesn't give you like 10 different examples. But at least, heuristically, we kind of expect metastability and as well as mixing time, because these two are just tightly connected to each other. They can scale exponentially in sort of this so-called free energy barrier, right? I think people working in error correction, this shouldn't be a surprising notion. And in particular, in 2D Ising model and toric codes, these things could be sort of scaling with the system size. If you're in one of the cohorts, you sort of hope that it takes just very, very long time to go to the other one. Right? So if you plug in this, it actually means that A could be sort of macroscopic. Yeah. So this exponential factor isn't that bad, right? If you sort of have a big also a comparable barrier. Okay, all makes sense. And of course, if epsilon is too small, it's approaching 0 or just already past the mixing time, then you're just looking at a Gibbs state. So then, our result doesn't say much. Okay, so here is one example. It's actually an extremely simple example where this sort of exponential scaling is qualitatively saturated, not exactly, but sort of up to polynomials. So the claim is that your hard disk that you use to store information is almost a volume law. Right? That shouldn't be a surprise. So how does that actually work? Right? So what ends up happening is that you really just take like slightly larger sizes of Ising models and then put independent ones. Right? And then the information you can store just scale with how many there are. So it would be the volume, not the area. Okay, so that sort of validates sort of our claim. And you can play with the parameter, right? So this correlation actually is validated, right? Because whoever copied the information holds all the true answers, so there's lots of correlation. But it's also exponentially metastable, right? And then so the lifetime here scale with the size of the length, right? And then if you pick this C to be 0.1, then it would be some kind of exponential scaling. And that would still break the area law. So in this example, really the obstruction of proving a stronger metastability area law is really because you need to somehow mix up this region. And here really the barrier is the length of this Ising model.
I thought A bar was the outside of A.
Yes. Right, in this case, I'm cooking up a virtual, like, I have this system and I just copy the same thing. So I'm copying a hard disk. So the bits sort of bitwise correlates. Yeah, so imagine you have two hard disks that holds the same exactly. You start with the same initial, like really the same data, and you ask sort of how, you know.
I get that, but
Yeah.
shouldn't the theorem be restricted to setting where A is, say, a disk?
A is
a ball, metric ball that respects all the. Wouldn't that be more meaningful setting? Here you are basically choosing the A to be a subsystem however you like.
Yep. What, do you mean to enlarge this outside, or?
No, I mean, there is an underlying metric which is a two-dimensional.
Yes, yes, yes.
But so, and A here is only slicing off the one half of that two slices.
Oh yeah, yeah, right. I guess you could also put it any way. You could, you could arrange this outside anyway. But roughly, up to constants, the boundary is still pretty much smaller than the volume.
No, that's not what I meant. But
okay.
Let me take it offline.
Okay, thanks.
Super naive question. Is this like a classical example?
Yes, this is 2D Ising models.
Okay.
This is fully classical. Yeah.
Okay, but to some extent, that calls into question what does it mean to have an area law, I suppose?
Yeah. So I guess the catch is that somehow the distinction between like ground state area law and mixed state area law is that here for mixed state you really have to also take care of the classical correlation, because it seems hard to remove that part. Yeah. So our result also holds for classical, fully classical systems. Okay. So therefore, what this exponential scaling cannot be qualitatively improved, even just by it is already matched by this classical example. Maybe the precise scaling could be improved, but it couldn't in general. Okay.
So the fact that epsilon scales with the mixing time, in the previous study suggested that if the epsilon is smaller than the 1 over mixing time, then it definitely has mixed. But is it clear that epsilon cannot be much larger than 1 over mixing time in the metastable state?
I mean, it could be much larger, but it has to be very close to the Gibbs state.
I'm just saying, imagine epsilon was not scaling like this, was something parametrically larger. Would your argument still hold?
Oh yeah, I mean, epsilon, the smaller the better.
Smaller,
yeah. It just that the bound become, if epsilon is too small, then you can use the original Gibbs state area law already.
Sorry, I think I missed the point you made. So if the mixing time is too long, then you cannot have an area law? Is that the conclusion?
Oh no, then you could have a better area laws, because it could be more metastable. Right? If these guys are bigger, then it would kind of be more metastable. Okay, so okay, I should accelerate. So now we take a step back and just to have high-level view of where does this area law come from, right? Because for mixed state is maybe a little less familiar with pure people. So as I already said, if you look at the classical Gibbs states, people don't really talk about area laws, right? But because it's actually very simple to get just from Markov property, right? Because if everything just depends on a boundary, certainly it has to have area law. So this is not surprising. But it turns out this route doesn't quite work for the quantum case. But these people still prove it, and then they have to go through this quite mysterious argument of variational argument for free energy. Somehow, the Gibbs state, which minimizes the free energy, must somehow balance energy and entropy. So that somehow gives you a hold on entropy. So that's kind of mysterious. And then our approach to this actually requires both of these ideas. We need both of this idea of local Markov property. We have to actually do this and so taking up most of the length of the paper. But we also need this idea of local minimum. So we somehow need these two in combination to actually get the area law. Something is very subtle about using this local Markov property. Okay, so now I'm going to dive in a little bit into the classical argument. So let's study this a bit more carefully. So let's try to repeat the classical metastability area law. Right? The argument fits in this slide. So suppose here's this region A. You want to sort of know how much correlation there is outside, that is sort of correlated with the outside regions. Right? And to see the area law, there's a combination of two facts. First is that if your metastable, say, is so globally, stationary under so hitting everyone, it must actually also be stationary, approximately stationary under sort of individual ones. Okay, so it means that kind of for any subset of these dynamics you hit, is actually must also be stationary. But then this sort of allows you to introduce the following hypothetic scenario. So you can say, okay, let me just run a hypothetic global dynamics only on this region and fix the boundary. And the claim is that this is just a finite dimensional Markov chain you're running out, condition on the boundary. So it must eventually resample the interior condition on the boundary. Okay, so combining these two, you realize the state must actually already have been Markov for these two to be consistent. Okay, so this sort of introduces like a natural view of this Markov property. So this conditional independence, you can think of this in a very dynamical way, where it is equivalent to say the set can be sort of resampled by the boundary. And then it does, it's okay if someone actually try to change the value of these spins, but since all the data is kind of already in a boundary, you can resample it. Right, so this is sort of like an error correction way of saying conditional independence. Okay.
You expect like a conditional Gibbs measure or something that you said like very early on about like condition on spins or something that's still a Gibbs measure on the inside, at least for like classical stuff.
I mean, effectively, if someone already fixed a boundary, then it just become another, global Hamiltonian, right? Because you already evaluate these spins, and then you just end up with a new Hamiltonian, and you're just sort of running Gibbs something on that new Hamiltonian, and you do this for every conditioning. Okay. Okay, so here, really the upshot is by thinking about these dynamics, it gives you like a sort of this recovery picture that someone disturbed this thing, you can always just recover it using the boundary. So then it's actually area law because all the data is just in the boundary. And then quantumly, this ends up being like the right way to try to generalize. And then here we need to we have used this resampling idea from this paper 3 months ago. So yes, you can define such a resampling map, and physically it kind of means that you put fires under this subset of qubits instead of doing it in everywhere. And then mathematically it means that it's the sum over sort of these terms that center around each spins, right? So you just select a subset of the lambdatians. Okay. I'm not going to show you what this is. It's defined in the paper. It's a little hard to show here. But roughly, this is what it wants to do, right? It wants to, in continuous time, it wants to do these local updates, just like the global dynamics. But it do some quantum rewinding or reweighting of the transition so that you get detailed bands. So this is like a more somewhat complicated quantum process. And to do this, it somehow spreads out the locality a little bit. Okay. So just to a vague intuition. Okay. And then and here are actually some classical, some technical differences from the classical case. So we actually have to define this time averaging. We have to introduce this 1/t and integral over t. So it's like sampling a random uniform time. That somehow is needed. But in any case, this map fixes the Gibbs state. So it has detailed bands. Okay, so it's still somewhat like a resampling map. But here are several kind of annoying features of trying to do this. Right. So first, classically we often think about condition on the subsystem, but quantumly you can't. Right. There's no such a general way to condition or print a quantum system without severely destroying a system. Right. So this is a very basic abstraction. Okay. And then this is sort of very closely related to the fact that if you know this, right, this is some kind of locality measure in quantum dynamics. That often you just get something that's quasi-local. Everything kind of have like a decaying tail, and this is sort of related to the fact that you have to energy measurements requires time, and then this often just make the dynamics kind of quasi-local. Okay. And at the same time, because you can't exactly condition, you actually also back react to the boundary. So that seems kind of annoying, right? And you have to be careful about how you choose these times. But in any case, so the rough picture is that yes, you can resample, but then you kind of have to smear out a bit. The boundary kind of gets bigger. Right?
So is this statement that the Gibbs state is a steady state of R for any subregion A, a kind of frustration-free condition?
Yeah, you can think of, yeah. Detailed balance is somehow, yeah. Exactly.
Oh, I see.
Yeah,
okay,
yeah.
Right.
Yeah, it's consistent with detailed balance. Yeah. And really that's why detailed balance is so nice. You could pick anything and then you can force it to be kind of have the same stationary state. That's sort of the nice thing about detailed balance. And it's also same here for quantum case.
Wait, so but this is satisfied for the time averaged object, but not for LA?
It's true for everything here. So each of them is detailed band. So then everything you do remains.
Right.
Yeah. Okay. So and then because of this sort of quasi-locality, because this boundary actually smear out so much. Very ironically, even proving this kind of resampling actually works for Gibbs state. This is actually quite hard. There's a recent paper with me and Kambi's. It does not recover the existing area law. Right? This was done like a long time ago, and they get this like such a clean bound, and they say that the correlation is somehow order 1 or order beta around this boundary, but here it's kind of smeared out so badly. So somehow we must be missing one ingredient to formally relate this to. Now, this thing is way too thick. Okay, so it turns out we need this other idea from the original proof of thermal area law. Is to think about free energy. I never imagined I would actually need to write down free energy in any of my paper, but this is what it is, right? It's for any quantum states, you can define a free energy as being the energy term minus temperature times entropy. And in particular, unlike the energy, this is not linear. So it seems that I would always try to avoid these kind of objects. But somehow this is really the right picture to reason about these entropic quantities. So in this paper, they show this very sneaky identity. So they consider the free energy of sort of the Gibbs state, and then some other state that's being defined by kind of taking the marginals of the individual systems. And then once you subtract them, somehow the mutual information just pops out. And then, this is really just isolating the entropy term and the energy terms. And then magic happens. when you say, oh, the Gibbs state must minimize the free energy. So you can put this inequality. And you move terms to prove the area law. So the proof of thermal area law is just this line. It's kind of amazing. But it's also not very clear what's happening.
What does it mean, f of sigma a bar tensor sigma a? What does it's like you remove the boundary, you take a Gibbs.
All right, this is the individual marginals. Right, yeah. So you can, the marginal is sigma a, and then the marginal of the boundary is a bar. Yeah. And you just somehow, yeah, so something violent must somehow happen between the boundary. Yeah. Yeah, but a priori, it may not be clear what, how to compare these two. Right, this is just some completely arbitrary object. But then the claim is that because Gibbs state is a minimum, you can compare with any state, including this state. So it's a pretty slick argument. Okay, and inspiration from here is to look at this very carefully and realize you kind of don't need a true minimum, a true global minimum to do this, right? So anything that has this property is just fine. So we will kind of want to say this as really only requiring some kind of local minima against erasure, right? Because this is really what it is doing, right? You kind of remove this part A and then you put it back some state here. And it turns out, as already hinted, this local minimum of free energy is precisely the Markov property. Okay, so here's the animation. So you can imagine, so the metastable state is sitting here in one of the wells. And then when you do this erasure, it must perturb it in some way. Right? You kind of wiggle the probability distribution. It's now out of equilibrium. And then the claim is that when you run this local resampling dynamics, it somehow kind of recovers to something that's very close to the metastable state, but it might have leaked out a little bit. And the claim is that this procedure, the possibility of this procedure is really a manifestation of local minima of free energy. It's really because this map R is monotonically decreasing free energy by data processing. So therefore, the only way for this to happen is that this erasure must have raised the free energy for you to be able to come back. Yeah, and then you write this down, and then you conclude the proof of area law by the existing argument.
So here you need like the stronger local Markov property where the boundary region is small, or can you just plug in the...
Right, the beauty of this is you're not directly talking about locality of the map. You're somehow using a free energy as to avoid talking about the smeared boundary. Yeah, so here really what we're using is to go through this free energy and say the free energy decrease. And so from here you gain locality, then you recover as area law.
What do you mean by local erasure?
Oh, it just means this. Yeah, you take your state, you basically trace out this thing inside, and then you put back like a not correlated state. So this is what we call it erasure. You're kind of destroying all the correlation between your state. Intuitively, you're kind of comparing these two, right? And somehow, when you evaluate the mutual information, this kind of tells you how much correlation there are between these two subsystems. Yeah. So yeah, the local Markov property, and then going through this free energy, it altogether gives the area law. Okay. Right, so it ends up a lot of the paper is devoted to proving this local Markov property, and then this argument I show you actually is like 1 or 2 pages, like very clean, but all the technical difficulty reduces to proving this statement. Just to recap, I already kind of said it a few times, but the thing we want to prove is that if you have a metastable state, someone destroy this part and replace with with anything here. You want to apply a recovery map that could be somewhat non-local, But then you wanted to recover the state. Okay, so this is the Markov property. It's also like a dynamical way to think about quantum conditional dependence. And then, if you look at this seems very similar to what we have seen, and this is really the dominant source of error. Is because you somehow want to recover this region, and that then requires some kind of local mixing process to fully kind of resample this quantum region.
So does your earlier example about 2D Ising models imply that global quantum Markov property shouldn't be true?
What was the question?
Because if you were able to improve the e to the a factor in the local Markov property, you could have got a better.
Well, you say this a classical Ising model example violate anything?
Sorry, would that?
Oh, I guess it couldn't, because classically you do have Markov properties. You have global Markov. Yeah, classically you do have. Yeah.
Sorry, I'm a bit unclear what you bought in the second factor you increase free energy, because usually if you're analyzed, your free energy barrier, or your metastable state is going to have an epsilon times delta H. And so plugging in this, you can only choose A to be some size. And so if you go into poly K, that would also be size poly delta H or something.
Okay, the question is about how big could A be, I guess.
I guess the question is if you have an example of a model
where this is tight.
And your previous results where the Chem-base is not tight enough.
But I think this also is consistent, more or less consistent with the Ising model example. So if we take this to be A, like square root A, that would matches the Ising model.
Yeah, but in the few slides ago, you said that your result with Chem-base was not good enough because it was
Yeah. So that's right. Yeah. So yeah, that's right. Because of the statement is that because of this factor, this thing becomes pretty fat, and this seems generally true, and it seems to be somewhat generic true whenever you want to think about metastability. So I don't know if, but I do believe it can be somewhat improved in particular physical system, but I don't know if there's a general, you should expect a general bound. Okay, so I'm very close to the end. Okay, so I'll just quickly sketch how this at all work. So a very technical problem is that if you want to look at this very, very carefully, one technical issue is that we're all dealing with these metastable states, right? We're not dealing with the true equilibrium. And then when you do this, do this erasure and you try to recover it, why doesn't it just drift away to another local minimum? Now, this turns out to be very technical and requires for us to build other framework to characterize why this is not happening. Right? So you somehow have some sense of it wants to restore to the same kind of local minima. Even you do this pretty violent erasure and then recover. And then we have to prove some other things. Let me show you some very cool equations that I don't expect you to understand it immediately, but it's just very cool. Okay, so one very nice idea that at least I really like is like a fundamental identity for the entropy production. Right, so when you evolve your state, your free energy decreases. Right, so you can look at this object. Also, it's actually equal to the entropy production rate. I guess for the relative entropy production rate. And it turns out we need to introduce. We need a very explicit form of this thing. So for those who have worked in similar areas, this is some version of the Fisher information. So I think some people got very excited whenever I say Fisher information. And this is the version for KMS detail balanced Lindblad family we considered. Okay, so it looks kind of crazy because it has some gradient of log of the density matrix. Right? This is, this seems completely crazy object, but this identity is true. Seems kind of crazy that this is needed, but it sort of has a root in, it's also called like the de Bruijn's identity that you can trace all the way back to 1D diffusion. So this is some version of gradients of log likelihood ratio. So it actually have a pretty deep root. Okay. So if you like, I'm sure some of the people who like feature information will find this curious. Okay. But this log is kind of hard to use, this log sigma. It's hard to use, and we end up having to introduce this other condition that somehow is a little bit more workable, that captures some sense, some very static sense, where the metastable state is locally thermal. And it ends up, so the thing that we really require is this kind of thing, this kind of equation, that you want to freely pass a local operator through your metastable states, and you want this to be possible as long as you compensate it with right factor of the Gibbs state. Somehow this is the right, it is a version of what's being locally thermal. Okay, so this actually it plays a role in the proof of Markov property. So important that we actually give a symbol for this, and then we have to prove that whenever the feature information is small, so entropy is slow changing, it must also be approximate detailed bands. Okay, so just to give a flavor of how the argument work. Okay, so here's the end of my talk. I think hopefully I'm not substantially over time. But really, to me, I would say this project is trying to, it seems to point out a theory of quantum metastability that wants to be explored. The audience has already asked, what are bottlenecks? What are these old nice classical notions? And we really only explore part of it. We define this feature information, approximate detailed bands, but we don't think we really have a full picture of quantum metastability yet. Okay, and then another thing is, the audience has already asked, it seems that the picture of area law here is a bit different from ground state area laws, and it would be very nice to clarify that. Because here we have nothing like a spectral gap. Everything we have is slow mixing. There's this epsilon parameter. So it will be very curious to try to understand whether they're the same thing or not. And I'll just stop here. Thank you.
We've eaten into our break a little bit, so maybe we'll take questions offline and ask Anthony during the break. And we'll come back at 10 after-ish.